So in 6.3, we're going to be talking about the idea of the inverse of the exponential function. So the question then becomes, what is the inverse of f of x equals 2 to the x? Well, we learned earlier when we talked about inverses that inverses are reflections across the line y equals 2x. So if I were to reflect my points across the line y equals x, I would get, instead of the point 0, 1, I interchange my x and my y, I get 1, 0. We also know that the exponential function has a horizontal asymptote at y equals 0. Well, if I interchange my x and my y for that, that means the inverse function is going to have a vertical asymptote at x equals 0. So then based on those, we get that the graph of our inverse function is going to have to look something like this. So we had our laundry list of facts from our previous section that we know about the exponential function. So for our exponential function, it's continuous, we know its domain, we know its range, its horizontal asymptote, it always contains this point, and increasing and decreasing. Turns out that for the inverse function, we know all of these same things because we know them for the original. So for the inverse, of b to the x, 1, we know it is continuous. We know that its domain, since we're interchanging x's and y's, its domain is going to be the range of the exponential, and its range is going to be the domain of the exponential. So we're going to have its domain has to be the set from 0 to positive infinity. Its range has to be then from negative infinity to infinity. As we saw above, if we reflect a horizontal asymptote across the line y equals x, or interchange x and y, we get a vertical asymptote. And we get x is equal to 0. So let's see what else we had. It always contained the point 0, 1, and then we had some stuff on increasing and decreasing. So if we interchange our point, then this will always contain the point instead of 0, 1, it will always contain the point 1, 0. We'll leave the other two off for now as we continue to talk about this. So let's go ahead and try to find the inverse of f of x equals 2 to the x. So the first step in finding inverses is 1. We replace f of x with y. So that gives us y equals 2 to the x. Step 2 is we interchange x and y. So that gives us x is equal to 2 to the y. Then step 3 is we need to solve for y. But here we run into a little bit of a problem. The question then becomes, how do we isolate y? The y is an exponent on the base 2. And up until now, we do not have a method on how to do this. So let's describe this verbally. So what does our equation say? The input x, or rather, the output y, is the exponent on the base 2 in order to get the input x. So the input x so our output is the exponent on the base of 2 that we would need to use in order to have the input x. That's our verbal description of our inverse function. So let's formally define our logarithm base a. So let's start with our symbol. So we have log base a of x. So the a is the base of the logarithm. The x is the input, or what we call the argument. The logarithm so the first thing we want to take note of is a logarithm is an exponent. It asks the question, what exponent goes on the base a to get the number x? All right, so let's go ahead and look at a couple of examples. So find the logarithm base 2 of 1024. So the question is, well, what exponent goes on 2 to get 1024? Well, let's see. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. I'll write this out really long. So 2 times 2, which is 2 squared. So 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. And finally, 2 to the 10th power is 1024. So what was the exponent that I needed to get 1024? Well, 10. So the logarithm base 2 of 1024 is equal to 10 because 2 to the 10th power is equal to 1024. The logarithm is the exponent that goes on the base in order to get the input x, because the logarithm is the inverse function of the exponential. All right, it's now your turn. Go ahead and find the logarithm base 3 of 729. All right, so let's go ahead and resolve this. So what exponent would I put on 3 to get 729? Let's see, 3 squared is 9. 3 cubed is 27. 3 to the 4th is 81. 3 to the 5th is 343. Nope, it is not. 243. And 3 to the 6th is then going to be 729. So then it looks like our exponent is going to be 6. So the logarithm base 3 of 729 is equal to 6 because three to the 6th power is equal to 729. All right, so the logarithm is an exponent. All right, so let's take a look at our next thing, which is we want to talk about exponential and logarithmic form. So as we've just seen, exponentials and logarithms are inverses of each other. And if we have something in the form a raised to the b power is equal to the number c, this is referred to as its exponential form. If we want to compare that to its logarithmic form, we can rearrange it using this pattern that we see up here. So if our base is a, we see that the base of the exponent is the same as the base in the logarithm. So the equivalent form would be the logarithm with a base of a, and what goes inside the logarithm was what was on the other side of the equal sign. So the logarithm base a of c is going to be equal to the number b. Well, that should make sense because b was the exponent. And what is a logarithm? A logarithm is the exponent. So log base a of c is equal to b because that is the exponent on the base of a. So if we need to rewrite something in exponential or logarithmic form, we can interchange these two at will because they are equivalent. So raised to the b power equals c is mathematically equivalent to the logarithm base a of c equals to b. All right, so let's take a look at example number 2. So we wish to convert the following to a logarithmic equation. So one thing we want to take note of, the x is in the exponent. So if we identify our a, b, and c, our a is 6, our b is x, and our c is 7. So then we rewrite this in its equivalent logarithmic form. We have the logarithm with a base of 6 of 7 is equal to x. When we rewrote the equation in logarithmic form, the x is now isolated. All right, it's now your turn. Go ahead and give you try number 2 a go. So convert to an exponential equation. The logarithm base 8 of x squared plus 1 is equal to 2. All right, so let's go ahead and resolve this. So if we start and identify our bits this time, we have our logarithm and we want to convert to an exponential. So our base is going to be 8. Our c is the argument of the logarithm, which is x squared plus 1. And our b is going to be 2. So the base in the logarithm is the same as the base of the exponential. So we have 8 raised to the b power, which is 2, is equal to c, which is x squared plus 1. So notice in this one, the opposite thing happened that was in the previous example. In example 2, our variable was trapped inside of an exponential. It was the exponent. And when we rewrote it in logarithmic form, our variable was now free to be isolated. In this example, our variable x was trapped inside the logarithm. But when we rewrote it in exponential form, we would now be able to solve this equation for x. The x is no longer trapped in a logarithm, and we would be able to continue to resolve using any of the techniques that we have done before. All right. So now, we were simplifying some logarithms earlier, and you may have noticed that they happen to work out. Well, that may have led us to ask the following question. Well, how would I simplify the logarithm base 5 of 30? So the question is what exponent do I put on 5 to get 30? Well, let's start. 5 to the first power is 5. 5 squared is 25. 5 to the third power is 125. So we notice we have a bit of a problem. We have 5 to the x, and we want to know what that is, but it's 30. So we see the value is in between 2 and 3. So we're going to have to come up with another method to help us find what that is exactly. So all we can say definitively right now is that we know that x is somewhere between 2 and 3, and we would probably guess that it is closer to the value of 2 than it is to the value of 3. All right, well, we'll go ahead and stop here today, a few minutes early, well, almost 15. All right, so the first thing we're going to start talking about today is some notations involved with logarithms. So the first one we want to talk about is the common logarithm. So the common logarithm is the logarithm base 10. So this is our default base for a logarithm. So our convention is the following. If a logarithm is written without a base, we assume the base is 10. So in symbols, if we have just log x, this really means logarithm base 10 of x. So just like with a square root, we don't write the index of 2. When we have a base of 10 on a logarithm, we do not write the base, we just write log, and we infer that it should be base 10. So there is another logarithm called the natural logarithm. And the natural logarithm has a base of e, where e is Euler's number. So that was the number we talked about last time that was about 2.718281828 blah 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 on forever. So this logarithm is special, and it's so special in fact that it gets its own symbol. So we write ln for the natural logarithm of x, and this is the symbol we will use for the logarithm base e of x. So we will always write ln x, not log base e of x. So the natural logarithm gets its own symbol, and that symbol is ln. And it just stands for the logarithm with the base of e. So now, if we take a look at our, we'll notice on the left-hand side as we go down, we actually have both of these logarithmic buttons on our calculator. Every scientific calculator will always have a base 10 logarithm, so a log without a base, so base 10, and the ln, which is the natural logarithm, and they will both be present on our calculator. All right, let's take a look at our next example. So the magnitude of an earthquake on the Richter scale is defined as R is equal to log of I divided by I naught, where I naught is the minimum measurable intensity of an earthquake, and I is the intensity of the earthquake. The Tohoku earthquake in Japan in 2011 had an intensity of 10 to the 9th times I naught at its epicenter. What was the magnitude of the earthquake? So before we answer the question, let's talk a little bit about what the Richter scale does. So this is actually fairly common for a lot of different scales in science, pH, and other things. We notice that the Richter scale is defined in terms of a logarithm. So if I have a magnitude 5 earthquake, and it changes to a magnitude 6, how many times more intense is that earthquake going to be? Well, what is it that the logarithm represents again? It's an exponent. And what's the base on our logarithm? 10. So if our exponent on our base increases by 1, that means it would be 10 times as intense. If we have an earthquake that increases from a 5 to a 7, well, what was the change on the Richter scale? Well, 2. So that means the exponent changed by 2. So 10 squared gives us 100. So when an earthquake changes from a 5 to a 7 on the Richter scale, the 7 is 100 times as intense as a 5. So when we're talking about things like Richter scale or pH, we need to be aware that we're using a logarithmic scale. And that makes changes that are very big seem very, very small, right? So a change from a 5 to an 8 would then be 1,000 times as intense. So each time the Richter scale increases by 1, you're getting an earthquake that is 10 times as intense because it's measuring the change on the exponent. So as I mentioned, pH is also measured on a logarithmic scale. Decibels, so sound intensity, is also measured on a logarithmic scale. So a lot of these things grow a lot faster than we would think because they are logarithms and not linear growth. All right, so now back to our problem. It says that the earthquake had an intensity of 10 to the 9th times I naught at its epicenter. And we want to calculate its magnitude. So R is going to be the logarithm of 10 to the 9th times I naught divided by I naught. The I naughts would reduce out, and we just get the logarithm of 10 to the 9th power. So what is the logarithm of 10 to the 9th power going to be? Well, what's the question that it asks? Well, what exponent do I put on the base of 10 in order to get 10 raised to the 9th power? Should be 9, right? Remember, the logarithm is the exponent, right? So it's the exponent on the base of 10 that we would need to get 10 raised to the 9th power. Well, it better be 9. All right.